Things are okay?
What's your life?
Okay.
How you did the 1, 2, 3, 4, 5, 6, 7, 8. How you do that? Like, I was trying.
Oh, how to do it quickly? Oh, sure. Ooh. So if I just want 1 and 2 and then so you just want to get the okay. So just type in the first 2 in the pattern. And then highlight them both. And then just pull.
Oh,
yeah. Yep. You're welcome. Ooh, and then I just copied it all the way across because apparently I dragged it. Anyway, other questions? All right. So last time we talked about Newton's method, right? So let's think about how we might use Newton's method to solve a relatively straightforward. Oh, I'm so sorry.
You're all right. Sorry for being late.
No worries. Thanks for not putting a doorknob to my kidney. So let's think about how we can use Newton's method to solve a particular type of problem. So, for example, pardon me, goodness. Let's think about things that your calculators can't do. What do I mean by that? Well, your calculator is a piece of machinery, piece of computing machinery, I guess I should say. All your computers, all your calculators know how to do is turn things on and off. Actually, more accurately, high or low charge. Okay. On, off, right? That's all it knows how to do. So basically, anything that we can represent by doing on, off, we can do. Anything that we can't do by on, off, we have to approximate. Okay. Basically, is kind of the rule. All right. So using on, off, you can add. Right? If I can add, I can multiply. I can also subtract. But other things are really hard for computers to do. For example, division is hard. Division takes longer than addition or multiplication does. Right? We'll talk a little bit about that. It really does. It's longer to divide things than other operations. But other operations that you just can't do exactly would be like taking the sign of something. You can't do it exactly on a calculator. Okay? You can't do, pardon me, you can't do exponentials on a calculator, e to the x or that, or you can't do log of x. But part of the problem is just how numbers are represented, and part of the problem is that the functions themselves aren't what's referred to as algebraic. But let me just give you a quick example here of what I mean by representations are difficult. I should have loaded. I hit the wrong one. Cancel. Switch accounts. There we go. Cancel. Oh, new notebook. Okay. Maybe. All right. So that number is pretty easy to represent in a decimal system, right? So is that one. Okay. Watch what happens when I calculate it after it loads everything up. Sometime this century when it loads something up. Like I said, I should have loaded this up to start with. Ooh, yeah, super fast. Just to load all the kernel information to start with. Oh, for heaven's sake, I'll just open up a different Python IDE at this point. Good grief. Yeah, it's still saying it's trying to connect. All right. Well, we'll let that go for a while, and let's see if I can get another IDE opened here. Hold on. Do I have it on the desktop? I do not. Okay. Oh, there it went. Okay, good. All right. That looks weird, doesn't it? Okay. Part of the problem is that, again, we're representing things with on and off, zeros and ones. They have to be in binary before you can represent it in the computer. And the issue is that something like 0.1 or 0.2 is a repeating decimal. Decimal implies base 10, so I did quotes. Okay, so repeating decimal in binary. Whether you have a repeating decimal, it has to be cut off somewhere, which means that the representation of 1/10 in your computer is not 1/10. It's something really, really close to 1/10, but it's not 1/10. Same problem with 2/10. Okay. So that's what the issue is, and we've got these different errors, and we're going to talk more about these errors later. But again, the issue is that your things have to be represented with things that can be on and off, right? So another thing that is hard for a computer to do would be doing square roots. Okay. Everything needs to be a really good approximation. And we'll talk about how good approximations are later. But let's think about how we could use Newton's method to approximate a square root. Now let's literally think about what the words are. Newton's method helps us find roots, right? So if I wanted to approximate the square root of, say, 5, what function could I find the root of to help me find the square root of 5? I want to find a function that has a root that is equal to square root of 5. What function, easy function, can you come up with that has a root of square root of 5? Square root of 5. It's all right, I want literally, you should be able to give me an explicit function that has a root that's the square root of 5. Square root of 5. Square root of 5. The reason why I'm emphasizing square. Function square as a root of square root of 5. If I'm saying function and square, what function do you think I'm trying to get you to say? Oh, good. Quadratic square. Squaring, right? Can you come up with a quadratic function, a squaring function, that has a root that's equal to square root of 5? So don't overthink it. Literally start with x squared. How can I move it to where it has a root of square root of 5? Hey, x squared minus 5. Yeah. Yeah. Yep. Exactly. All right. So if you let f of x equal x squared minus 5, that has a root that's equal to square root of 5, right? Agreed? True is one way to get there. That's okay. All right. It also has a root of negative root 5, right? So if we wanted to actually do positive root 5 versus negative root 5, it's going to depend on where we make our guess to start with, right? All right. So what was the format for Newton's method? Good. Yep. So your next one in the sequence is the previous one minus, what was it again? Yeah, the function over the derivative, right? Oops. Oops. So I can get my prime in the right spot. Good. That's our Newton's method, right? We have to have a starting point. Once we have a starting point, we can get going. Keep going. What did we say we have to worry about? Yeah, if you've got derivatives that are close to 0, you're going to get large things that you're subtracting, right? Dividing by things that are really, really small, things really, really big. If you actually divide by 0, you're going to have an issue, big issue, right? But even if you have a small issue, right, it can throw off what you're trying to look for. What I mean by that, for example, is let's say so x squared minus I don't know why that did that. X squared minus 5 looks like that, doesn't it? Okay. And say we were trying to find square root of 5. If you start, well, in general, if you start over here, you're going to have a problem anyway. Go away. Okay. But if you start over here, that's, say, again, remember when we did tangent lines, right? If we start that's really, really close to that vertex of that parabola, your tangent line is really, 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 really flat. And remember, again, we're looking for the root of this tangent line. Now we're way over here, right? You could imagine if we had a different scenario, not this specific function, but you could imagine a scenario, well, actually, this scenario will work. Now I'm over here. I'm going to use tangent lines that are over here, and I'm going to end up finding this root instead. Right? So if I'm really, really close to a spot where it's really, really flat, I might not ever find the 0. I might find another 0 that I wasn't looking for. Okay? There's going to be issues. So we need to worry about these zeros in that denominator up there. Okay? That's why I said sometimes you'll see mixed methods for actually solving these, finding roots of functions. It'll use some bracketing methods like bisection method, which always works, right? We said that last time. It always works. It's just slower. We'd like to use Newton's method if we can, because Newton's method is faster, right? So sometimes you'll see bisection method used for a while to narrow down your interval, and then apply Newton's method to make it fast. Okay. So you'll see these mixed methods of solving these things. All right, anyway. Notice that I said we wanted to do square root of 5 from this function. Now I've got a function that's easily representable, right? I've got squaring. Squaring is just multiplication. Multiplication is something that we can do on a calculator, computer, easily, right? And then subtracting 5. So those are good things that we can do, and this should get us an approximation of square root of 5 pretty quickly. So if we're doing this with by hand a little bit, let's just do a couple by hand, or a little bit by hand here. All right, so I'm using a different one to write on today. It wants to, when I put my hand down, it wants me to type for some reason. All right, so let's say I set up a table here. This is going to be a pretty small table. Our first guess over here, can you give me something that you know is close to square root of 5? 2 works, right? Do we want, by the way, do we want to use 0? No, 0 would be bad for the derivative, right? Because that's the vertex of the parabola. But 2 is close, right? All right, so to be able to apply Newton's method now, we need to make sure that we can not only calculate the function, but we also need to calculate the derivative of the function, right? But the derivative here is pretty straightforward. What is the derivative? 2x, right? So your f of x, again, was x squared minus 5. Our derivative is 2x. So your x of n plus 1, your next x will be 0 minus, we plug in 2, we get what? Negative 1 on top, right? 4 minus 5. Plug in 2 on bottom, we get 4, so we get, do that right? Oh, yeah, x and s 2. Thank you. That's what, 2 plus a 4, there we go. 2.25. Good. Thank you. I knew that wasn't making any sense because we started close. Thank you. I was putting in the n value. It's x of n. All right. That's what I get for labeling my steps. All right. So your next x of n here is 2.25. You plug it in again. At this point, we're going to probably use a calculator. So you would have, on the numerator, you would have 2.25 squared minus a 5 And then, what you have, 4.5 for the denominator? Yeah. By the way, unfortunately, I don't have calculator display on this thing, I don't think. I don't think I have a calculator display on here. Oh, for heaven's sake. I do not. Okay. I'll just write it down. If you, on your calculator, just type in 2 and then hit enter, so your 2 comes up over here. You can do this quickly by just using your previous answer key, because you remember you're just kind of pulling it into the next one, right? So if you type in answer minus answer squared minus 5 over 2 times answer, and just hit enter several times, you should get the approximations, and it should settle down pretty quickly. Because I don't have a calculator with me, because I didn't think I think the numerical analysis class, I didn't think to bring a calculator. I have a computer, so I don't really think about it. But on your calculator, you can do it pretty quickly. If you type the function with putting the previous answer in it on top, and the derivative of the function with the previous answer in it, you'll do it quickly. You can literally just hit enter over and over again, and eventually you should get the same decimal coming out over and over again. It's nice that we've got this iterative method for Newton's method that we can do that way. Anybody get the next value in my sequence? Oh my goodness. Do you have the next value in the sequence?
2.236.
2.236. And then if we do the next one, and 2.236 again. How quickly did it settle down before your decimal stopped changing? Yeah, 3 steps? Yeah. And if you put in square root of 5 in your calculator, does it agree with all the way out? Yeah, better. Otherwise, we've done something really wrong. Otherwise, I might as well just cancel class and go on. So, darn for you. Yeah, Newton's method is really, really fast. By the way, this is indicative of what I would expect you to do on a quiz, by the way, being able to do a few steps of this kind of method. One of the reasons why I wanted to do it. But we can approximate square root really, really quickly. And this is exactly what your calculators are doing. The square root function is not actually built into your calculator. You've got these approximations that are built in your calculator that they can do it quickly. So the point. Right. But you can do these for cube roots. If you wanted a cube root of the number, same idea, right? What function would you use if you wanted a cube root of a function? I didn't want to go through that again. We get an x cubed, right? So if you want a cube root of 11, you would use x cubed minus 11, right? I mean, honestly, you could use any function that has cube root of 11 as an answer for a root. The idea is to be able to do it with operations that your calculator can do easily. That's the whole point. All right, so that's just applications of Newton's method. It's really, hopefully, pretty straightforward to use. We'll code up a little bit in Python, make sure that we know how to do it in Python as well here in a minute. But I want to talk about the other method I actually asked you to think about for today. Okay. So we used Newton's method and we needed the derivative, right, to be able to apply it, which means that if I'm going to use it for whatever reason, not only do I need to know the function, I need to know the derivative of the function as well, right? So I said that, can we come up with a method where we don't need to find the derivative. And I said, think back to calculus class and how you develop tangent lines. What'd you come up with? Secant lines, right? Secant lines can give us approximations to derivatives, right? So that's exactly what we can do here. And this is actually called the secant method. All right. So let's compare it to what we said for Newton's method, right? For Newton's method, we said we've got some function. Here's its root. We used a single point and drew it down with a tangent line and used that for our approximation, right? That was Newton. Yeah. Okay. For the secant method, redraw the picture here. For heaven's sake, stop it. All right. For a secant method, if I need a secant line, how many points do I need to find a secant line? 2, right? So to use secant method, we need 2 initial guesses, whatever they happen to be. And then again, we would use the slope of the tangent line, right? Or excuse me, not the slope of the tangent line. We'll draw the secant line through those 2 points. And again, I have to change computer because it's really starting to frustrate me. Stop. Again, that would be our approximation for our root. Well, assuming I drew that through those 2 points. Okay. All right. So, much like what we did last time, we used a line to approximate the function and then found the root of the line, right? For the tangent line, we used the derivative to find the slope of the tangent line and use point-slope form. Here we don't have a derivative to find the slope of the line, but I do have 2 points, right? So if I want the slope of the secant line, say this is, for the love of Pete, okay. Say this is my x1 and this is my x2. What would I do to find the slope of that line now? If this is my y equals f of x. Okay, and then how do you find your y's? You're right, it's y2 over y1 minus y, but how do I find the y's? Good, yeah, plug the x's into the function, right? So your slope of your secant line is f of x2 minus f of x1 over x2 minus x1, right? Now remember when we did the tangent line, just to write down the equation, that was y minus f of x1 equals f prime of x1 times x minus x1, right? We agree with that? Okay. If I want to do the secant line, I've got a couple of options. But I still need to fill in the same things for point and slope, right? Let's do the easier one first. Let's do the slope. We just found it, right? So your slope, where the f prime is going to be, will be your f of x2 minus f of x1 over x2 minus x1, right? We agree? Okay. Now, the idea behind this is we want this to be iterative, right? Last time we said that x2, when we did Newton's method, x2 was x1 minus f of x1 over f prime of x1. And then x3 was x2 minus f of x2 over f prime of x2, right? Then those subscripts going up, right? When we do point slope form and we have 2 points, I could use either the x1 or the x2, right? The way I've got the subscripts numbered, I'm going to use the x2 in this case, and so I want to get rid of the x1. So I'll start with x1 and x2. Then my next step I'll have x2 and x3. The next step will be x3 and x4, and so on down the line. That make sense? Okay. So when we do this, I'll use x2 here and x2 here. But we would solve it in exactly the same way. Right? Remember we found the x-intercept, we put in 0 for y and solved for x? The only thing that's changing is the fact that I've changed this slope to this one. Right? So when you do the secant method, so I don't have to go through all of those details again, your next one in the sequence, the x sub n plus 1, will be the previous one in the sequence, x sub n, minus the function of the previous one in the sequence. That's the same numerator as what we had for Newton's method, right? But the denominator is going to be our new slope. Our new slope was f of xn minus f of xn minus 1 over xn minus 1. Again, dangers that you would have here. One danger is that your f of xn is equal to your f of xn minus 1, or they're close together. Same idea as when we had the derivative was 0, or the derivative was close to 0. That also means that you're going to have issues with this particular method once your points start getting, your function values start getting close to each other. Right? We want them to get close to each other because I'm trying to find a root. We want them both close to 0, right? We want them to converge to 0. If you let it go too far, you're going to get issues with the denominator and have problems, right? So you're going to want to have a cutoff somewhere in this, right? But if you keep going, eventually you're going to end up dividing by a 0, right? Didn't necessarily have that problem when we did Newton's method. Why didn't we have that problem when we did Newton's method? Well, this is brought on the board rather than on the computer. If we have what's referred to as a simple root versus a multiple root, remember a simple root is that it basically crosses the x-axis versus a multiple root, it comes and touches and goes on. If we have a simple root, the closer we get, my derivative stays fine. It doesn't get really, really close to 0. It gets really, really close to some value, right? But it doesn't get close to 0 necessarily, right? Now, if I have multiple roots are bad for lots of reasons. But if I had a multiple root, then I'm going to have issues with Newton's method, right? Yeah. Anyway, but for the secant method, I'm not using the derivative. I'm using this as my approximation for the derivative. And one of the things that I have to compute is that subtraction. Yeah? That subtraction is going to be really, really close to 0 the closer I get to the root. And if I start dividing by that for the next case, if it gets too small, if they're too close together, it's going to cause me some approximation issues, which we'll get into more later. Okay? So a lot of times you'll see methods that make your tolerance doesn't necessarily have to be that they agree like out to 15 decimal places, right? Maybe 8 decimal places is enough. Maybe 5 decimal places is enough, right? You'll see these tolerances cut off earlier because you don't want them to get too close together and things blow up again and make your thing crash. Okay. So it's just something to be careful of if you're programming these things, or even using built-in methods of Python. They can still have issues if you don't set your tolerances right. These are things you have to worry about. Lots of things can happen when you're trying to approximate things. Anyway, we're going to talk more about them as we go along. But anyway, this is the formula. Okay? So let's see if we can apply this to... Yeah, let's do it in Excel first, and then we'll play around with Python a little bit. So, let's try. Let's just do e to the x plus x again. I think that was one of the ones we did last time. Okay. So, I'm going to leave off the n part for this one. Let's say we have, no, maybe I won't. We'll do n and x sub n minus 1 and x sub n. Let's do f of x sub n. Oops. Minus 1. I'm just trying to label the columns for us here. F of x sub n. And we'll just write slope of secant. And we'll do x sub n plus 1. All right, so again, if we're going to do something like e to the x plus x, it'd be kind of nice to know about where the 0 is to start with. So maybe you do a bracketing method to use your first couple of points. But notice even with using secant method, you don't have to bracket the 0 where the root is, right? Because again, I'm going to pick 2 points, draw the line through those 2 points, and then use the next, the 0 as our approximation, and then just get rid of the one of the old points and try the next 2. That's the idea, right? So you don't have to be on either side of the 0. You just want both of them to be relatively close to the 0. Okay? So again, let's say we use e to the x plus x. I think we got something that was on the negative side, right? If I remember correctly. Doesn't matter. We'll see what happens when we actually solve this. Okay. Let's just try 0 and 1 to start with. See what happens. Worst thing that happens is it doesn't work. We try something different. We're not going to blow up the computer to try it. Well, we shouldn't blow up the computer to try it. Okay. All right. So again, e to the x plus x. So e to the b2 plus b2. That's f of x of n minus 1. The reason why I labeled it as x of n minus 1 is that's the one I'm going to replace, right? That's the one I'm going to replace with the x of n. So when we go to the next line, I'm going to move this x of n here. Okay? When I calculate my new x of n plus 1, I'm going to move this one to here when we get to that point. Okay? Things are going to get shifted over. Does that make sense? Okay. All right. So that was f of... Can you see this okay, or do I need to zoom in more? Should ask that. If I need to zoom in more on something, please tell me, because I tend to forget. Okay. All right. F of x of n is literally the same formula, just moved over one, right? So I can actually just copy and paste, and that should give me the right thing. You can check it. Go back in here. It really is the right thing, right? Since we have them lined up next to each other, I can just copy and paste it over to the next one since we're using the relative cell references. Slope of the secant line. Only doing that as a separate, you don't have to do it as a separate one. You can type it all in one big long cell. I just thought it'd be a little nicer to see each piece. Okay. All right, so slope of the secant line is f of x sub n, which is an E2, minus f of x of n minus 1, which is E1, or sorry, try that again, D2. Make sure you have parentheses in there, right? Divided by x of n minus x of n minus 1. Is okay? All right. How do we find our next one? We use the previous one minus the function value for the previous one divided by the slope of the secant line. That was why I calculated the slope separately, right? It would have looked like a really garbled up formula. Not a gobbled up formula. Apparently it's lunchtime. I'm hungry. It would look really garbled, right? If I try to type, you can do it all in one step. I don't care, but I wanted to make it look a little bit nicer. And not have to worry so much about nested parentheses. Those are always a pain. Everybody okay with how we have this set up so far? Okay. Again, like I said before, I'm going to take the x sub n, it becomes the new x sub n minus 1, right? So where I have x sub n minus 1 in in the next row, I'm grabbing the x sub n from the previous row. Okay? Oops. And for my x sub n, that's going to be my new x sub n plus 1, right? That's moving over. So those are just getting copied down to the next row. And now we should be able to just copy paste. Highlight that row, the end of the row, copy it down. Now highlight the whole row and pull. And this is what I was just mentioning a little bit ago. What happened in row 9?
Got a division by 0.
We got a division by 0 here, didn't we? Because our roots got close. Once our roots get close to where they're supposed to be, the function values are essentially the same. They're both 0. I subtract 2 zeros from each other, I get 0. Try to divide by it, and catastrophic things happen. Right? This is why I said that eventually you need to make sure you cut things off where you're happy to cut them off. Cutting it off here probably was good enough, right? I didn't need to keep going. But I should agree with what we got last time. I'm pretty sure this is the same function that we got. Notice it's a little slower than Newton's method, right? It's a little slower than Newton's method, but faster than bisection. Okay. So bisection method, we said, has linear convergence, right? And Newton's method, what's called quadratic convergence. It's a constant multiple of the square of the error for the next step. The secant method has what's referred to as superlinear convergence. It's in between. It's about 1.6 power on your error. It gives you the next one, rather than the square. I'm not going to go through that now. Maybe not at all, but definitely not going to go through it now. Okay. Just know that it's faster than bisection. It's faster than linear, but not as fast as Newton. Okay. Questions on that at all? Basically, it is Newton's method, except we're using the secant line to approximate the derivative. It's pretty much the same method, otherwise. All right, let's see if we can code it up. See if we can code these up. Live coding is always a little bit dicey, but we'll try it. Okay. All right. Let's see if we can code these up in Python. Let's do all 3 of them that we've done so far. We've done bisection method, we've done Newton's method, we've done secant method. So bisection method requires a function, which I'll call f, and it requires a bracketing points, right? We need to start somewhere. Now, we're not going to do any error checking when you write these things. You probably should do error checking as well. For example, when we call this function, we should probably check that we really have bracketed the root. And if we haven't, we should get an error message back to the user saying, hey, you didn't bracket the root, right? Because the method we come up with is assuming we have a sign change, okay? That would be good programming logic, right? Making sure you error check. I'm not going to worry about that today. Okay? But know that for like a final product type of thing, you should be doing error checking as you're putting things up. If you're doing something that's programming. Okay? I just want to make sure I mentioned that. Okay. All right. Well, let's just do it. So let's assume that things are bracketed. What did we do first? We will need the function values, but what did we do for our new guess for bisection? I guess I should say that. Yeah, we did the midpoint, right? Yep. Okay. So I'll just call it M x1 plus. Oops. Don't capitalize my x. X1 plus x2 over 2. Now let me ask you, because this is a programming decision. Do you want to loop inside the bisection method, or do you want to loop and then call the bisection method each time? I don't care which. I'm just asking before you want to write it today. We can either loop in the bisection method and return the answer, or we can return the two values that we're going to use for the next bracket. What you want to do? That's fine. We can do that. All right. So, do I want to use a for loop or a while loop? I probably want to use a while loop, right? Because I'm trying to get my points close together, right? So, let's be fancy. Let's say we'll let the user pass in a tolerance, but let's say we'll define one as a default, so if they don't pass in a tolerance, we'll just use 10 to the negative fifth. I want a negative sign on my exponent. Oops. Use 10 to the negative fifth. If you haven't used Python before, it's okay. Know that you have to use a double asterisk for power. I can tell you from experience that one of the most annoying things is that I'll put a caret in there because I use everything else I use as a damn caret. This one doesn't. Okay. So can't tell you how many errors I've made in programming because I can't use the damn double asterisk to get my power. All right. So probably might as well do our while loop outside of this, because if I'm already indent that, if I'm already within the tolerance, there's no reason to go through the loop, right? And just return what I need. So I want to make sure that my bracket has whatever length, right? Is what if my length is too big, I want to have it, right? Okay. So let's use absolute value of x1 minus x2 is greater than the tolerance. There's no reason to even calculate the midpoint if I'm within my tolerance, right? As a matter of fact, when we're done, we'll just go ahead and just return the midpoint. We know we're definitely within what we want. Okay? We're at the end. All right, so let's calculate the midpoint. Now, like Masana said, we're going to need to calculate some function values, right? What was our check to see if we still had a sign change or not? What did we do? Yeah, they're multiplied, right? So if f of x1 times f of m is greater than 0. Oops, let's do, it doesn't matter. Do greater than 0. You can do also less than 0. It gives you the sign change. So if we do f of x1 and multiply by the f of the midpoint and it gets greater than 0, get the sign change between the two. Does f of x1 and f of m have the same sign or different signs if the product is greater than 0? Same, right? They're the same sign, right? So is the root between x1 and m or m and x2? M and x2, right? Because that's what sign change is, right? It's not between x1 and m. So which one do we want to replace? Do we want to replace x1 or do we want to replace x2? x1, right? What are we going to replace x1 with? The m, the midpoint, right? We're going to move it over to the midpoint, right? So if there's not a sign change, then x1 equals m, right? And leave x2 alone, right? Agreed? Okay. Otherwise, x2 is m. Isn't that how we set it up in Excel? We use that if statement, right? And now I got a whole list of things that I can select from there. Oh, one of the, I suppose maybe one of the nice things, maybe not, with if you use Google Colab, you can pair Gemini with it, their AI, whatever, interface, whatever word I'm looking for. And Gemini will give you suggestions on how to complete things in the code. Now, like I've said before, you have to be careful with AI because it'll tell you things that are wrong. Okay? I've played around with Google Colab and have Gemini suggest things to me, and it was so wrong so often that I just turned it off. It was so annoying. Okay? So, if it's something that you're interested in playing around with, I would absolutely encourage you to play with it. Absolutely. But don't take it as gospel that it's giving you the right things by any stretch. In my experience. Okay. Like I said, I had it was on. I was taking classes last semester over at U of I. It was on when I started the semester, and it was off by like the second week of the semester because I couldn't stand it anymore. It was just so bad. Okay. Anyway. All right. So we're going to keep doing this over and over again until we're within the tolerance, right? And then when we're done, we'll exit the while loop and we will return. We'll just return the midpoint. So we'll return x1 plus x2 over 2. Just might as well go ahead and just take the one in the middle. Honestly, if you're within the tolerance at that point, you can return x1 or x2. I'm just going to take the one in the middle. Yeah. All right. If you're in Google Colab, you can hit the play button, or if you hit Shift and Enter, it'll run it automatically. I prefer the keystrokes because I think it's faster. Again, I don't care if you use this or not. Use your own. If you're comfortable with a different IDE, use the other IDE. Fine. Okay. I just think this is nice because it doesn't require me to download an IDE. Again, students can sign up for the Pro version for free. The Pro version allows you to different acceleration engines. If you've got something big, it'll go faster. And then you're not using your computational power necessarily on your laptop or what have you. So anyway, there's the method. Let's see if it works. Let's define our function. Oh, I need to do math functions typically are not automatically entered into Python, so we'll import numpy. Many of you are probably already familiar with this. All right. So define our function. We use the e to the x plus x, right? When you say import numpy, numpy has a bunch of different whole ton of different functionality pieces that will get imported. In particular, it'll basically import any functions on your graphing calculator. When you say import numpy as NP, it just gives you an abbreviation to refer to them on it. So you don't have to type numpy dot whatever every time you want to call it. You can just do NP dot whatever they call it. EXP is your exponential. So NP dot EXP will give you your natural exponential function. One weirdness about Python and other programming languages is that if you have a natural log, it's always LOG. No, I shouldn't say always. Most times it's LOG instead of LN. So if you got things with natural log in it, be careful of that too. All right, so let's run this. The function we already wrote was bisect, right? We want to pass the function that we just wrote. We need two initial guesses that bracketed it. The root was between -1 and 0, right? It was negative 0.5 something. We just did it a minute ago, didn't we? Okay. All right, so -1 and 0 I'll use to bracket it. And I got the answer for us. That should agree with what we just had on Excel. If we want to see what's going on at each step, you could just print your x1 and x2 at each step to see the brackets changing. So if I go back up here and put in a print statement and rerun it, and that shows you the brackets all the way down. Oh, yeah, that did it. That's interesting. Yeah, well, that's right. I only set it to 5 decimal places. That's why I quit. So you can at least see the brackets changing each time. And you can notice that at each time it's only changing one of your inputs. What questions do you have? So far, so good? Let's do the same thing, but let's do Newton. Oops, if I can spell Newton. What do I need to pass into a Newton function? For bisection, I need a function and 2 points, right? 2 points that were bracketed. And again, we did not do any error checking, right? I'm not going to worry about error checking here either. But if I need to do error checking here, what should I probably check for if I was doing Newton's method? Derivative, right? What about the derivative piece? All right. So what do I need to pass into Newton? I need to pass it a function and how many points? Just one, right? There's even one starting point, right? All right. So I'll give it a function name of f, and but I also need what else if I'm doing Newton's method? Not only do I need a function, I need its derivative, right? So I better pass a derivative too. So I'll call that function df, and then I'll pass an x into it, the starting point. Okay. So if we're going to do this, when we do Newton's method later on, we defined our function, our e to the x plus x, right? We'll also need to define our derivative of that function as well, so we can pass it. Okay. Oh, and I probably also should put some tolerance level in here as well. I'll make it a little bit smaller this time. I get all the equals does is just give you a default value if you want, but it allows the user to change the tolerance if they want to when they call the function. They don't have to do it, but they can. I'm guessing I'm telling you stuff that you already know, at least most of you. Okay. All right. So, what should we do first? I like Java's idea of doing a while loop, but I need to check if we're getting close to a root, right? In the previous one, I could start in the while loop because I could check to see if the 2 points were already close together, right? I don't have 2 points in this case. So before I start my while loop, I better get the next guess. Or not the next guess, but the next iterate, right? We agree? Okay. So I'll call it x sub new, just to give it a name. You can call it whatever you want. How do we get the next iterate? What do we do? For Newton's method, how do you get the next iterate? What's the formula? We'll get function over the derivative, right? So we're passing in the x value. So it'll be x minus f of x over the derivative of x, which I'm passing in the function as df. We'll calculate the new one. What should our condition be for our while loop in this case? I don't think I need that. Yeah, I probably do. What should the condition be here? Well, let's look at what it was before. I looked at how I wanted to make sure my bracket length was greater than the tolerance, and then I kept looping, right? What do you think we should do here?
Absolute value of x sub n minus x.
Good. And greater than your tolerance? Yeah, good. Good. Same idea, right? I'm looking to make sure that two consecutive iterates are still far enough apart, or too far away from my root, right? Agreed? What do I want to do? Yeah.
Set x equal to x sub nu,
Okay.
and then calculate the new x sub nu.
Good. I agree. It's pretty much what we did in Excel, isn't it? In Excel, we copied and pasted it down, right? And then calculated off of that. The copying and pasting in this case is making the x value that you want the new one, right? All right, that's literally all we need, right? You want to look through it every time until the two are close enough together. And then we're done. We'll just return the x sub nu. That should do it. All right. We already defined our function above, but we did not define our derivative, correct? So our function was e to the x plus x. So our derivative here will be e to the x plus 1. I could have called it f and df as well. I just gave it a different name so we weren't confusing the two. You can call it whatever you want, I don't care. Let me tell you, it's a huge benefit nowadays to be able to program. When I first started learning, everything was a single letter. You got more variables. So you were out in 28.6. So you also well, at least when I learned on, you had line numbers that you had to put in to tell what lines it would do the line sequentially, but your function calls were called subroutines, and you had to say go to the subroutine that's at this line number, and then you return back to this line number, and it was fun. All right. Anyway, so let me go ahead and just define that. Then come back here, and we'll run Newton. Remember, we have to pass in the function and the derivative of the function and an initial starting value. So let's say we started at 0. Interesting. Came out and tell me it was a floating point number rather than just telling me what the number was. I don't know why. Off the top of my head. Anyway, there was our value. We should agree again with what we got for our root. Not 100% certain why it just said told me what the type of the value. I mean, it doesn't matter that it did. It's just I don't know why it did. Again, if you wanted to see the different values of what's going on, let's say we just put a print statement in here for our Newton's method and then rerun it. And at least we can see that it got done quickly. Even to 10 decimal places, right? I put the tolerance into 10 decimal places and it got done quickly. That is the benefit of using Newton's method. It's fast. This is okay. Now that we've got this, secant method should be pretty quick, right? Let me just see what things we need to change. All right, so if I change this to secant method, what do I need to change for what we pass into it? There's two things we need to change. Do I need to pass in the derivative for the secant method? No. So I can delete that out. What extra thing do I need to put in, though? Another point, right? All right, so I'll call it x2. Now that I have 2 points, I can do like what we did in the bisection method for our while loop, right? I can start it right away because I have 2 things I can compare, right? Okay, so let's do absolute value of x1 minus x2. Get rid of the print statement for the time being. Oops. Get rid of that statement. Oops, I did it again. All right. What needs to happen now? Yes.
Start the slope.
Yeah, let's go. Okay, let's do the slope. Sure, we can do that first. Absolutely. So I'll just write it as slope equals f of x2 minus f of x1, oops, divided by x2 minus x1. Cool. It does make changing my next one pretty easy. If I leave my variable name as x new for the time being, what do I need to change this x to here? X2, good. And then this one would also get changed to x2. What's the denominator going to be now? Slope, good. Cool. All right, so that's the new one. Basically, we want to shift everything away, right? The new x1 is going to be the old x2. The new x2 will be the x new, right? We're going to shift things. So the new x1 is the old x2, and the new x2, oops, I can type, is the new x that we just found. Right? And when we're done, we can just return the x new like we have. That should work. I'm going to go ahead and put in a couple of print statements so that we can see what's going on with these. Just so we can see what the brackets look like as we go. Okay. And let's do that. And let's run secant of our function. And oops, let's start 0 and 1 again. I think that's what we did before, wasn't it? All right. There we go. And we get the same value once again, shockingly enough. These numbers that we got here, these numbers that we got here should be the same as what we got in Excel in those first couple of columns. They should match exactly. As a matter of fact, let me pull it out a little bit, and you should see that the decimals that you can see actually match in each line, which they should. I mean, we use the same formula, so they should match all the way down. What questions do you have? Questions? Was this live coding thing okay? Okay. Well, good. I'm glad it wasn't a waste of 50 minutes of your time. All right. All right, let's do one more application of Newton's method that will lead us into stuff that we're going to talk about on Tuesday, and that is using Newton's method for optimization. Okay? So when we do optimization, that means we're trying to find either a maximum or a minimum. Could be a global maximum, could be a local maximum, depending on what we're trying to look for. Okay? As you go forward with trying to do optimization, say even in multiple dimensions, you might be finding local minimums or local maximums when you want a global one. So, for example, if you're doing things with neural networks, you might find a local minimum when you really want a global one. Or other machine learning techniques, same kind of things can happen. So you might want to run multiple iterations using multiple different starting places and see what happens. That's a discussion for a different day, a different class. But Newton's method is a method to help you find optimization, mins and maxes, optimization things. And this is basically a Calc 1 concept. If you look for a max or a min in Calc 1, what did you look for? What was the first thing that you did if you were trying to find a max or a min? What's the first thing you did with any problem starting off in Calc 1, basically? Take a derivative. Wonderful. Basically, that's what you do in calculus, right? Here's a new function. Let's differentiate it. Here's a new function. Let's differentiate it. Right? Agree? Okay. What did you do with the derivative? You were looking for a max or a min. Yeah, set it equal to 0 and find its root, right? So if you're using Newton's method for optimization, it's literally the same process, except that you don't have to use, you're not looking for a 0 of the function, you're looking for a 0 of the derivative, right? So if you're doing Newton's method for optimization, if you're doing Newton's method for optimization, you're trying to find a root of y equals f prime of x, right? Not y equals f of x, but y equals f prime of x. Correct? Okay. So your original Newton's method looks like that, right? That's for finding a root of f of x, correct? I can do two really, really fast things, both are exactly the same, and make this what you need to do for optimization. Rather than finding a root of f of x, I need to find a root of f prime of x. What do I need to do to this formula to change it? To find a root of f prime versus a root of f? Yeah. Put a prime here, put an extra prime here. There it is, the end. This is Newton's method for doing optimization. It's root finding of the derivative. Literally the same formula, right? Just taking the derivative. So, if I wanted to do this relatively quickly, I'm going to grab my Newton's method here. Paste it. Again, I'm going to need to pass it the derivative and the second derivative, right? So I'm just, well, it doesn't matter. This is Newton's method. I'm going to just change the names really quickly so that we don't get it confused with the original one. So I'm just putting an extra D in front of each of these, right? I mean, it's literally the same method. So if you know to pass in the right functions, then you don't have to do this change. Okay, I'm only doing it to illustrate the formula. Okay. Right. So in this case, let's do a different function. The function that I'm going to use, I'll call it f1, is, I'll do x to the fourth. Let's do plus an x squared minus a 3x and a plus a 1. I need to define the derivative. Derivative of x to the fourth is 4x cubed. Derivative of x squared is 2x, and derivative of 3x is just 3. And then I need to take the second derivative, so I need the derivative of that. That'll be 12x squared plus 2. Assuming I did all my derivatives correctly. And finally, let's do the optimization here. I need my derivative and my second derivative and a starting point. This should be okay. Got about 7.728-ish. Okay. So I'll leave this on the screen so I don't get rid of it for you. Oops. Well, I thought I was going to leave it on the screen. Let me go back over on Desmos real quick and show you what the graph of the function looks like. X to the fourth plus x squared minus 3x plus a 1. Zoom in over here. Let's move this over. And if I go here, well, didn't do what I wanted it to do. That's okay. Anyway, you can see that's pretty close to where the minimum is. And I really did get negative 7.28082. And you can see that really does look like in the graph that was where the minimum was. Again, a fast method for doing it. relatively speaking. Again, all we're doing is finding a root of the first derivative. It doesn't tell you if it's a max or min, it's just finding a root of the first derivative. But this is using Newton's method for optimization. Literally the same function. The only reason why I wrote a new function was just to make it match the formula. You could have just used the old Newton's method formula and passed in the right functions. That's okay? All right. Next time, we will do another optimization technique, which is a bracketing technique, much like the bisection method is. Okay. The bracketing technique we'll use is actually used in practice for finding optimizations for multidimensional functions. Okay. It's referred to as the golden search. If you're familiar with the golden ratio, it's related to that. Okay. And then we'll also talk a little bit about representation in numbers and pitfalls of that and errors, kind of things like we talked about at the beginning of class today. So that's the idea for Tuesday. All right. Have a good one. See you then.